All right, this is R7. Here we're going to talk about rational expressions. So to start off with, the quotient of two polynomials, P and Q cannot be equal to 0, because it's going to go in the denominator, right, is called a rational expression. So quotient means we're dividing P by Q. Okay, and this might look like something like this. X plus 6 divided by x plus 2. That's a very simple binomial over a binomial. Or it might be a little bit more complicated. We might have two factors on the top and two factors on the bottom. X plus 6 and x plus 4 divided by x plus 2 times x plus 4. Or it might be given in the form 2p squared plus 7p minus 4 over something like 5p squared plus 20p. So these are all rational expressions. Rational just means it's a fraction, it's a ratio of two polynomials. Okay? So the first thing you might want to have to do is find the domain of a rational expression. So the domain of a rational expression consists of all real numbers except those that make the denominator 0, right? Because that would make this expression undefined. So we can find these numbers, these problematic numbers, by just setting the denominator equal to 0 and solving for that variable. Okay? So for example, if we had x plus 6 over x plus 2, you would take that x plus 2, you set it equal to 0, and let's solve for x. Minus 2 from both sides. X equals negative 2. That cannot be in the domain of this rational expression, because if we plug in negative 2, it's going to make the denominator 0, and that will be a problem. Okay? So the domain is going to be every other x value except for x equals negative 2. Everything else is perfectly permissible. Okay? Now let's look at example B. You've got x plus 6 plus x plus 4 divided by x plus 4 plus x plus 2. So now you have two factors in the denominator here, x plus 4 and x plus 2. Now either one of these factors might have an x value that could turn this whole thing into 0. Okay? So we're going to use something called the zero product property to find what makes the denominator in this case equal to 0. So how does this work? So if you have a times b equal to 0 in general, then either a is the thing that equals 0 and made this whole term 0, or it was b that was equal to 0 and made this whole term 0. Okay? So we have to investigate both possibilities. So you've got x plus 4 times x plus 2 is equal to 0. Well, then either it's the x plus 4 that's equal to 0, or it's the x plus 2 that's equal to 0. Now, in order for x plus 4 to be equal to 0, x would have to equal negative 4. In order for x plus 2 to equal 0, just like we saw in the last example, x would have to be negative 2. Okay, so both negative 4 and negative 2 are problematic values. Okay, so the domain is going to be all real numbers except for x equals negative 4 and x equals negative 2. Okay? Now, you might have also noticed in this example that you have an x plus 4 up top, right? So why can't we just cancel these two factors and simplify this? Well, if we do that, then we're actually going to be changing the function. Okay, so we would be left with x plus 6 over x plus 2. That would be fine. X plus 6 over x plus 2 is fine when x is equal to negative 4. It doesn't have a problem. But this is not the function that we're starting with, right? So we had an x plus 4 in the denominator. We cannot have x is equal to negative 4 here, okay? So just be careful of that. You don't want to accidentally cancel out one of these factors when you're thinking about domain specifically. Okay, so we want to make sure we're understanding what are those problematic values. Don't just cancel it out and just only think that x cannot be negative 2. It also cannot be negative 4 in the original function, okay? Next, let's talk about the lowest terms of a rational expression, right? So we are just talking about canceling factors out and things like that to reduce this. So let's see what this might look like. We've got a fundamental principle of fractions here. A times c over b times c is equal to a over b. assuming that neither b nor c equals 0. Okay, so all that's going on here is we're canceling out the c that's common to both the top and the bottom. Okay, and no, the thing that we're canceling out, we're saying that thing cannot have been 0. Okay, because that would have caused a problem in this original factor. Okay, so let's see if we can apply this and write each of the following expressions in the lowest terms. So in example C, we've got 2x squared plus 7x minus 4. Well, we can go ahead, we can factor the top. That's going to give us 2x minus 1 times x plus 4, and you would do this via your AC method that we went over last class. And the bottom, well, we're just looking for the greatest common factor. Both have a multiple of 5 to give out. Both have at least one x to give out, so we can factor out a 5x. So we'll be left with x plus 4 in the denominator as well. Okay, so we notice that, well, we have an x plus 4 on the top, we have an x plus 4 on the bottom. We can go ahead and we can cancel out that common factor. And we will be left with 2x minus 1 over 5x. But I want to make a note. So remember, just like we had done before, the way this was going, in the denominator, two values that would have been problematic are x equals 0, because that would turn this 5x equals 0, and x is equal to negative 4. So even though you've reduced this, in the domain, x can be all real numbers, but still cannot be 0, and it still cannot be negative 4. Okay? Even though that x plus 4 isn't there anymore, because we canceled it, because we started with that in our expression, x still cannot be equal to negative 4. So we have to add that exception, that rule in there. Okay? So just be mindful of that. Example D. 6 minus 3x over x squared minus 4. So let's see what this looks like in a factored format. From the top, we can pull out a 3 from both 6 and negative 3x. We'll be left with 2 minus x. In the bottom, that's our difference of squares. A squared minus b squared is going to be equal to a plus b times a minus b. So that factors to x plus 2 times x minus 2. Okay, great. Now, immediately, or as it is, it doesn't look like we can cancel anything out right away, right, from the top and the bottom. However, if we factor a negative 1 out of the top, then we can actually flip the order of this subtraction, right? So we have a difference here that's 2 minus x. If we factor out a negative 1, well, that x becomes negative. I'm sorry, that 2 becomes negative. The x becomes positive. So negative 2 plus x is the same thing as x minus 2. Okay? So now we've written this in the same format as what we have in the bottom. So now we've got an x minus 2 on the top, x minus 2 on the bottom. We can cancel this out. So all we had to do was factor out a negative. And you're only going to have to do this with a difference. So you don't have to do anything when you've got a plus sign. A plus b is the same thing as b plus a. However, a minus b is not the same thing as b minus a. You have to factor out that negative 1 in order to flip the order in a difference or a subtraction like this. Okay, so we cancel out that common factor. We're going to be left with just a negative 3 on the top and an x plus 2 on the bottom. And if anybody asked you what the domain of this was, you would still say, well, x cannot equal negative 2, but it also could not have equaled positive 2 because this factor was here to begin with. That would have made the original denominator 0. Okay? Now let's think about multiplying and dividing with rational expressions. So example E. We've got this complicated looking thing here. We've got 3m squared minus 2m minus 8 up top, divided by 3m squared plus 14m plus 8 on the bottom, all of it multiplied by 3m plus 2 over 3m plus 4. So our first step here, to keep things simple, is we would want to go ahead, we want to factor these both of these using our AC method. Okay? So if we went ahead and did that, we should get 3m plus 4 times m minus 2 up top. And on the bottom, 3m plus 2 times m minus 4. And right away we notice that we have common factors. In red, we've got the 3m plus 4 up here, 3m plus 4 down here. We've got in blue the 3m plus 2 and the 3m plus 2. And this is great, because if these appear on the opposite side of the division bar, just like we've been doing, we can cancel them. Okay, so multiplication just means put everything together. Everything's being multiplied on top, everything's being multiplied on the bottom. We can write them all in one giant fraction, and we can go ahead and we can cancel out the common factors. 3m plus 4 and 3m plus 2, and we'll simply be left with m minus 2 over m minus 4. Okay. And of course the same domain rule holds from before. Whatever it was that would have made both of these denominators equal to 0, that still is not in the domain of this simplified version. Alright, now let's look at a division example. Example F. So you've got 3p squared plus 11p minus 4 divided by 24p cubed minus 8p squared. All of that divided by this other fraction, 9p plus 36, over 24p to the fourth minus 36p cubed. Now, to start off with, let's just factor everything. Okay, let's just see how that looks. So do your AC method on this polynomial 3p squared plus 11p minus 4. You're going to get 3p minus 1 times p plus 4. On the bottom, factor out your 8 and your greatest common factor of p, which is p squared. You'll be left with 3p minus 1. So that's nice. Right away we already see the same factor on top and the same factor on the bottom. Here we can factor out a 9 from the numerator. We're going to get 9 times in parentheses p plus 4. On the bottom, we can, both of these are multiples of 12. We can take a 12 out, and we'll take the lower power of p out, which is p cubed. Okay? Now from here, we're going to apply what previously, when we were just dealing with normal fractions, we might have thought of as keep, change, flip, right? So you'd keep the first fraction, you'd change that division into a multiplication, and you'd flip the second fraction. And you just multiply straight across, and you get something like 4 over 6. So the same property holds when you're dealing with rational expressions. So even though these are variables and everything, they're still just fractions. So when you're dividing fractions, keep the first one as it is, change that division into a multiplication, and go ahead and flip your second fraction. And now, once we've done this, so all we're doing is this numerator is going on the bottom, this denominator is now going on the top. Let's put everything together into one fraction. Let's see what we can cancel out. I already see a p plus 4 up here and a p plus 4 down there, 3p minus 1 up there, 3p minus 1 down here. So when we put it all together, what does this look like? Right, so we've also got a p cubed up here and a p squared over here. So this red factor cancels out, the blue factor cancels out. This p cubed can be rewritten as p squared times p, and then that p squared and that p squared at the bottom are going to cancel out. We've got a little bit more we can do. So we've got 8 times 9 in the bottom here. That's going to become 72. 12 and 72 will reduce, so 12 over 72 is really just 1 over 6. So we're just going to be left with a 6 in the denominator. So p times 2p minus 3 up top, and just a 6 in the denominator. And that's what it's going to simplify to. Much cleaner than what we had originally started with. Okay, next we're going to look at addition and subtraction with these rational expressions. So in example G, we've got 5 over 9x squared plus 1 over 6x. Okay? So in this case, right, whenever we're, just like we were doing before with numbers and things like that in previous classes, right? If we wanted to add two fractions, we need to make sure that they have the same denominator before we can do anything. Right? So we're going to try to get these two denominators to look the same. Okay, let's first start off with prime factorization. Let's just see what's there, what's missing from one that the other has, and what's missing from the other that the first one has. So 9 is just going to become 3 times 3. We've got our x squared. This 6 is going to become 3 times 2, and we've got 1x here. So we need to introduce another factor of x here, and we need to find, well, we need to get a 2 here and an extra 3 here. Okay? That way we'll have a common denominator. So we'll multiply the first fraction by 2 over 2, which is the factor that it was missing in the bottom here. We'll multiply the second fraction by 3x over 3x. That way we'll have 2 x's in the bottom here, and we'll have that 3 times 2 times 3. This is going to give us our least common denominator. Our first fraction comes out to 10 over 18x squared. Our second fraction is 3x over 18x squared. These have now the same denominator. Go ahead and just add them straight up, right? So we're just going to add the numerators. They're still just going to both be out of 18x squared. 10 plus 3x over 18x squared. That's all. Now, if we have a subtraction, same idea holds. We're going to have to try to find a least common denominator before we can combine these two. Now we've got two different polynomials here as denominators. So again, let's go ahead, let's factor them, let's see what's here, what's missing, if they have anything in common to begin with. So the first one's going to factor to x plus 2 times x minus 1. The second one is going to factor to x minus 4 times x plus 3. So I don't see any common factors here. So that means we're going to have to introduce whatever either fraction is missing. So this first fraction is going to need both the x minus 4 and x plus 3 factors. So we're going to multiply it. And notice that whenever we do this, and we did this the same thing in the last problem, whatever we're trying to introduce in the bottom, we can't just multiply it on the bottom. We're going to be changing the value of whatever it is we're dealing with. So we have to put this as something over itself, because this is really just 1. And so is this. This is really just a 1. So we're always allowed to multiply by 1. We're not changing the value of anything, but we're rewriting 1 in a very convenient format that's going to allow us to get these least common denominators and simplify this in a way that makes sense to us. Okay, so that's exactly what we're doing here. So just always make sure that whatever you're doing to the bottom, you have to do the same thing to the top of this fraction. Okay, so we're introducing the missing factors here, x minus 4 and x plus 3. For the second one, we're going to introduce the other missing factors, which were x plus 2 and x minus 1. Okay. So I'm not going to FOIL these out or anything like that just yet. We just want to see all these factors put together. Okay, so the tops is going to become 3 times x minus 4 times x plus 3. And over here, it's going to be x plus 2 times x minus 1. And especially when you have a negative sign, make sure you keep things in parentheses. So if we had to distribute this, we would know to do that. Okay. And on the bottom, they now have the full common denominator of all of the factors, all 4 factors. Okay. So you could FOIL the tops out. You'd get 3 times x squared minus x minus 12 for the first fraction. These two FOILed out would become x squared plus x minus 2. And we can go ahead, we can simplify the top. I will just leave the bottom the same here. There's no real need to do anything here, but if we can factor and cancel out any common terms in the top, it's always nice to clean it up like that. Okay, so you're going to be left with 3x squared minus 3x minus 36 if we distribute this 3. And the second one, we're going to distribute this negative. We'll be dealing with negative x squared minus x plus 2. So this negative and negative will become positive. The 3x squared and negative 3x squared will become a positive 2x squared. Negative 3x, negative x will become negative 4x. Negative 36 plus 2 will become negative 34. Okay, so the only other thing you really could do here, if you want to, was just FOIL all of this out, distribute all of this, and cancel or combine any like terms, but it's not necessary to demonstrate what's really going on here. Okay, so this is a perfectly acceptable answer. All right, and the last topic we're going to talk about here is complex fractions. Okay, so let's look at example I. So complex fraction is when you've got a fraction within this overarching fraction that you already had to begin with. Now, that complicates things, so ideally we would prefer to just not have to deal with this in either case, right? So now when you've got a simple denominator like this of k for this fraction and this fraction, what we could potentially do is, well, why don't we just multiply the top of this whole thing by k and the bottom of this whole thing by k? And remember, k over k is just 1, so we're not changing the value of anything that we're given here of this expression. But this is going to be really convenient because once we distribute this k, that denominator should cancel out. And the same thing at the bottom, that denominator is going to cancel out. Okay. So you'll get 6k, and then 5 over k times k is just going to be 5, so minus 5. Same thing here, this is going to give you k. 5 over k times k is just going to give you 5. So this is how we simplify a complex fraction. That's all there was to do in this case. Okay. We'll look at one more example. So in example J, we've got a over a plus 1 up top plus 1 over a, all of that divided by 1 over a plus 1 over a plus 1. Okay, so let's think about this. So last time we had to multiply by the least common denominator, which was just k. The least common denominator here is going to be the combination of both of these individual denominators. So that'll be a times a plus 1. So we just have to put all the different factors together. That's exactly what we're going to do. So we're going to multiply the top of this fraction by a times a plus 1 and the bottom of this fraction by a times a plus 1. And remember, this whole thing is still just 1. So we're not doing anything to change the value of the expression. All right, we can go ahead and then distribute this on our next step. Same thing on the bottom. We're going to distribute this and let's see what this looks like. The idea is, by doing this, we should be able to eliminate all of the denominators that exist within this complex fraction. Okay? So we're going to have a times a plus 1 over here up top, this a times a plus 1 here, same thing on the bottom, and now I see this factor is going to cancel out with that one, this a is going to cancel out with that one, this a is going to cancel out with that one, and this a plus 1 is going to cancel out with that one. Okay, well, that's exactly what's going to happen here. So let's see what this simplifies to. Well, we'll have a times a, which is going to become a squared. And then we still have an a plus 1 over here. Okay, so we're going to be adding that a plus 1. I should note, so there's no more denominators here, right? So this, sort of the intermediate step here, is going to be, the top is just going to be a squared plus a plus 1. And the bottom is just going to be a plus 1 plus a. Okay, so that's what we were dealing with here. Okay, that's exactly what we see here. Just go ahead and combine these two a's, and we get 2a plus 1 in the bottom. So a squared plus a plus 1 over 2a plus 1. That's our complex fractions. All right, that's a wrap on R7.